Hello, welcome to today's lecture. We are still on chapter 12, 12.5. So first of all, exam one correction is due on Sunday. Exam 2 review submission due on Sunday. You can find exam 2 review questions on week 5 module. And exam 2 is on Sunday at 6 p.m. If you have any problem taking the exam on that day, just send an email to me, figure out. And solutions to quiz 3 is also posted on campus. And the format for exam correction is you write down your wrong answers on the left-hand side, you write down the correct answers on the right-hand side, and you explain why it was wrong in the first place. Okay, so chapter 12, we start talking about lines and planes and adding a new variable, a new parameter like t to explain the location of a particle in xy plane using that new variable. So for example, this is x and y. You can define a new variable, a new parameter like t, and say that, hey, x is a function of t and y is a function of t. Now this point, as the location of your particle includes two functions, xt, yt. They both depends on this new variable. You can say, okay, that new variable is time, or it's heat, or other parameters. And this is the curve along with your particle is moving. Very well. Today we're going to officially define equation of a line, define equation of a plane using parametric form. Definition. Equation of a line. First of all, we can define equation of a line using parameter t this way. We call it parametric equation of the line. Very well. This is defined as R. So let us define it this way. So let me just erase this part of the board. I'm going to explain that for now. Then I'm going to classify all of these equations for you. So R is equal to R sub 0 plus t times v. The second equation that you get is x minus x sub 0 divided by a equals to y minus y sub 0 divided by v equal to z minus z sub 0 divided by c. Equation of a line can be represented either a vector, or eventually you can add a parameter here and rewrite this. So I'm going to explain what's the connection between these two. First of all, let us start by using these three fractions that are equal to each other. So since these are all equal to each other, we can set them equal to a variable like t. We use a variable like t, and we say that, okay, suppose all of these fractions are equal to this new variable, x minus x sub 0 divided by a equals to t, y minus y sub 0 divided by b equals to t, and z minus z sub 0 divided by c is equal to t. So x as the first coordinate of your line is equal to x sub 0 plus at. Y is y sub 0 plus bt, and z is equal to z sub 0 plus ct. So what are these? Okay. Take a look at a line. Suppose I already know there is a line there is a line. Let us call this line V, which is just a vector. Okay, you have a vector in XYZ or XY plane, and this is your vector. So it has direction, it has magnitude. Very well. I'm saying that, okay, I'm going to use this vector and graph a line. I'm going to graph a line which is parallel to this vector. So this is a line. So since it's a line, it continues both sides. That's why I'm using two arrows to show that I have a line. Okay, this line is parallel to vector V. Okay, and I'm saying that this line passes through a point. Suppose my line passes a point x sub 0, y sub 0, z sub 0, and is parallel to this vector V. And it is parallel to vector V. So any vector, as I mentioned, has components, it has direction, and it has magnitude. Suppose this vector has components A, B, and C. So this is my vector, A, B, C. This line can be written as R equals to R sub 0 plus T times a vector V. This R is X, Y, Z. So vector R includes components X, Y, and Z, which is equal to R sub 0, which is the initial point, initial vector, X sub 0, Y sub 0, Z sub 0, plus, since it's parallel to this vector, it means that you can say that the slope of the line is a multiple of this vector, directional vector. So T as your variable times A, B, C. This is the vector definition of your line in three-dimensional space. So this is vector definition. So what I'm doing here, I'm saying that, okay, I can simplify this. I can write it in compact form as X, Y, Z, which is equal to, so let me put this in a box. So you know that it's the vector definition of your line. So I'm saying that X, Y, and Z is equal to, I'm going to distribute T into parentheses and add the first components, add the second components, and add the third components. What I get X sub 0 plus T times A, Y sub 0 plus T times B, and Z sub 0 plus T times C. Okay, that makes sense. Why not? Now you have two vectors that are equal to each other. X is equal to X sub 0 plus T times A. Y is equal to Y sub 0 plus T times B. And finally Z, which is equal to Z sub 0 plus T times C. This is called the parametric equation of line. Vector definition and parametric equation. As you can see, these two are equivalent to each other. Let's write down these equations here. Then we go over one example together. So V R is equal to R sub 0 plus, so T times V, or X minus X sub 0, X sub 0 plus AT, Y equals to Y sub 0 plus PT, and Z is equal to Z sub 0 plus C. Parametric equation or vector definition. There you go, one example for you. We are still on page 1. Sorry, example is on page 2. There you go. So this example says, find a vector equation and parametric equation for line. We have a line passes through this point 5, 1, 3, 5, 1, 3, and it's parallel to vector and parallel to vector I plus 4j minus 2k. There you go. So let us form the vector equation and parametric equation for this one. For vector equation, we know that R is equal to R sub 0, the point that your line passes through, plus T, your variable, times vector V, or X, Y, Z is equal to the point 5, 1, and 3 plus T, your parameter, your variable, parallel to vector 1, 4, and minus 2. Okay, so X, Y, and Z is nothing but T plus 5, 4T plus 1, and 3 minus 2T plus 3. So you can describe your R as, so you have 5 plus T in the direction of I, 4T plus 1 in the direction of J, and negative 2T plus 3 in the direction of Z-axis or K. So you can describe it this way. You can leave it as it is, or you can describe it this way. 5 plus T, I plus 1 plus 4T, J plus 3 minus 2T, K. So this is your vector equation. Parametric equation is not very hard. You're going to just directly use this to write parametric equation. So you know that X is equal to T plus 5. So X is T plus 5, and Y is equal to 4T plus 1, and your Z is equal to negative 2T plus 3. You can leave it as it is, or you can rewrite it as X minus 5 divided by 1 equals to Y minus 1 divided by 4 equals to Z minus 3 divided by minus 2. Sometimes they call it symmetric equation of a line. So parametric and symmetric. So since you want parametric equation to have t next to it, let's just put the flash with the arrow here, and this guy is symmetric equation. So for parametric equation, we're going to see t as the parameter there. Okay, another example for you. Okay, we're on page 3, this example. It says, find equation of a line passes through these 2 points. So find equation of line passes through 2 points. 2 for -1 and -3, and the other one is 3, -1 and 1. Very well. Here you have 2 points, and you want to write equation of a line passing through these 2 points. Note that you don't have v. V, or the directional vector, is missing. What is v? You only have 2 points. So in this case, if you have a missing directional vector, you're going to form a directional vector connecting these 2 points. So since v, or the direction vector, is missing, we're going to form v. How do we do that? So suppose this is your first point, A, and this is your second point, B. They're going to form A, B. The line passes through AB, and we're going to use this as our directional vector. So remember that we have to write down the components of the second point minus the elements of the first one. So here you have 3 minus 2, comma, minus 1, minus 4, comma, 1 minus 3. So v is equal to 1, -5, and 4. The rest is easy. You can take the first point, or you can take the second point and write down equation of your line. Suppose we take the first point. I'm going to show you if you use the second point, you get the exact same. Let us take A, 2, 4, minus 3. So R is equal to R sub 0, which is 2, 4, -3, plus T times V. You form your V, which is 1, -5, and 4. So your R is equal to 2 plus T, 4 minus 5T, and -3 plus 4T. Very well. You can write parametric equation, you can write symmetric equation. The symmetric equation, so let me write or here for you, is going to be x minus 2 divided by 1 equals to y minus 4 divided by minus 5 equals to z plus 3 divided by 4. So you can leave it as it is, or you can write symmetric equation, or you can just say that, hey, x is t plus 2, y is minus 5t plus 4, z is equal to 4t minus 3. So either of these, okay. You might say, what if I take the second point? What do I get there? Let us take B as the second point, 3 minus 1 and 1. Okay, our R is now equals to the beginning point, 3, negative 1 and 1, plus T, V, our V is equal to 1 minus 5 and 4. So our R is equal to 3 plus T, negative 1 minus 5T, and 1 plus 4T. Or you can write it this way. X minus 3 divided by 1 equals to y plus 1 divided by minus 5 equals to z minus 1 divided by 4. Or you can write the parametric equation. X is t plus 3, y is minus 5t plus 1, and z is 4t plus. Now here's a question. Question says, at what point, question, at what point this line passes x, y plane? Okay. So you have your xy plane. Remember that in xy plane, xy plane, this guy is equivalent saying that z is equal to 0. We don't have any z. So at what point this line passes xy plane? So this line passes xy plane when z is equal to 0. We have equation of this line. Let's use the symmetric equation. X minus 2, which is equal to y minus 4 over negative 5, which is equal to z plus 3 over 4. So instead of z, you're going to use 0. 0 plus 3 divided by. So what's the meaning of that? It means that we get two equations. X minus 2 is equal to 3/4, and y minus 4 divided by minus 5 is equal to 3/4. We're going to solve for x and also y. We're looking for a point, so you have x coordinate, y coordinate, and you already know z coordinate is equal to 0. So x is equal to 3/4 plus 2, so x is 11 over 4. This is your very first coordinate. And here you get y minus 4 equals to negative 15 over 4. So y is negative 15 over 4 plus 4, which is 1 over 4. So that point is 11 over 4, 1/4, and z is equal to 0. Very well. So let us talk about parallel, perpendicular, and skew lines. So note that for two lines, L1 and L2, suppose L1 has directional vector V1 and L2 has directional vector V2. We say that two lines are parallel to each other if V1 is parallel to V2. So these lines are parallel if and only if V1 is parallel to V2. V1 is parallel to V2. Of course, we say that two lines are perpendicular or orthogonal if V1 and V2 are parallel to each other. So L1, L2, V1, and V2. These lines are perpendicular if and only if V1 is perpendicular to V2. If you don't have parallel or perpendicular lines, you say that lines are skew. If lines L1 and L2 are not parallel or perpendicular, then we say we have skew line. Skew lines. So parallel, perpendicular, and skew lines. Let us go over one example, see what's going on here. We're on page 4. Example. Suppose you have these two lines, L1, which is given as x equals to 1 plus t, y is equal to -2 plus 3t, and z is equal to 4 minus t. For the second line, we're going to use a different parameter, like s. L2 is defined this way. You have 2 times s. X is 2 times s. Y is equal to 3 plus s. And z is equal to -3 plus 4s. Okay, our goal is to analyze these two lines. What's the relation between these two lines? Are they parallel to each other? Are they perpendicular to each other? Or you have skew lines? So let us find V1 and V2. Okay, V1 has components that are actually coefficients of your parameter. So V1 is 1 times t. So this is 1 times t, 3 times t, and plus minus 1 times t. So V1 is equal to 1, comma 3, comma minus 1. V2 is equal to all coefficients of your parameter, which in this case is s. So here you have 2 1 times S, and 4 times S. 2, 1, and 4. Okay. Here you have 2 vectors. Are they parallel to each other? Are they perpendicular to each other? So if V1 is parallel to V2, then they must be multiples of each other. What do I mean by that? For example, if you have the first vector like A as 1, 2, 5, the second vector, which is parallel to this vector, B, is going to be, for example, 2, 4, and 10. It means that B is equal to 2 times A. So if you divide the components, it must be equal to a fixed number. So if we divide the components, it must equal a fixed constant. Okay, let's check. Suppose we divide 1 by 2, 1 over 2. Is this guy equals to 3 divided by 1? Of course not. They are not equal to each other. So they are not parallel to each other. So V1 and V2 are not parallel. Well, perpendicular. If you form the dot product between these two, if they are perpendicular to each other, then the dot product is equal to 0. If V1 is perpendicular to V2, then dot product or inner product between V1 and V2 must be equal to 0. Is this true? Let's do the dot product. 1 times 2 plus 3 times 1 plus negative 1 times 4. So you have 2 plus 3 minus 4, 5 minus 4, which is equal to 1, not 0. So V1 and V2 are not perpendicular. V1 is not perpendicular to V2. So which case is this? It means that these two lines are skew lines. Okay, perfect. Let's write the equation of a plane, then go over some examples. Okay, definition of equation of a plane. To write the equation of a plane, you need a normal vector to that plane and a point passing through that normal vector and is on the surface of your plane. So, to write equation of the plane, we need a vector that we call a normal vector. We need a vector, normal vector, which is perpendicular to your plane. To the plane. We usually denote it by n, vector n, and one point on the plane, like x sub 0, y sub 0, z sub 0. Equation of a plane can be written this way. So if n is equal to a, b, c, the components of your normal vector, this is a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 equal to 0. So this is the official equation of a plane. This is your plane. This is your point, x sub 0, y sub 0, z sub 0, and this is your normal vector n, perpendicular to the graph of your plane. We can also distribute a into parentheses, b into parentheses, c into parentheses, and you get ax plus by plus cz, which is equal to a x sub 0 plus b y sub 0 plus c z sub 0. Usually, since this guy is just a number, we call it d. So ax plus by plus cz equals to d. Equation of your plane. So this is the official equation of your plane, and this is the simplified version. Okay, let us go over one example together, see what's going on here. Now on page 6. Example. This question says, find equation of a plane passing through the point 2, 4, negative 1, and normal vector is also given. We're lucky in this case, don't have to worry about anything. 2, 3, and 4. There you go. So to write the equation of a plane, we need our A, we need our B, we need our C, and also the point x sub 0, y sub 0, z sub 0. We have a nice formula for that. We know that it is A times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 equal to 0. Guys, you have to simplify after you substitute everything. So here you have 2 times x minus 2 plus 3 times y minus 4 plus c times z minus negative 1 equal to 0. So you get 2x minus 4 plus 3y minus 12 plus 4z plus 4 equal to 0. So you have 2x, 3y, 4z, 2x, 3y plus 4z, negative 4, negative 12, negative 16. Okay, you can cancel out these two, plus 12 equals to 12. This is the D that I wrote down here. Okay, let's graph this plane. We have 2x plus 3y plus 4z equals to 12. This is your plane. You can find the points of intersection with xy plane, with xz plane, with yz plane, but plug in x equal to 0, then you get 3y plus 4z equals to 12, or you can just set x and y equal to 0, then z is equal to 3. You can set z and y equal to 0, 2x is equal to 12, you get 6, and so on. So this is your plane. Of course, this plane continues. Another example for you. This example says, find the equation of a plane that passes through these points. The first point P, 1, 3, 2. The second point Q, 3, -1, and 6. And the last point R, which is 5, 2, and 3. 3 points. There is no normal vector here. So first, we need to find the normal vector. How are you going to do that? You're going to connect these 2 points, and find the cross product between them. You can take any 2 pairs, that's absolutely fine. Here, you can take, for example, PQ, PR. So we need to form 2 vectors. For example, PQ and PR. Then find cross product between these 2. We know that the cross product is perpendicular to the plane, including these 2 vectors, and we call it our normal vector. This is our goal. Okay, let us form PQ, PR, then the cross product. So PQ and PR. Q minus P. 3 minus 1, 2, -1 minus 3, -4, 6 minus 2, 4. This is your first vector, so let us use the symbol for a vector. And the second vector, PR. 5 minus 1, 4, 2 minus 3, -1, and 0 minus 2, -2. Now our n is equal to the cross product between these 2 vectors. PQ, PR. 2, -4 and 4, 4, -1 and -2, which is equal to I. You get 8 plus 4 minus j, -4 minus 16 plus k, -2 plus 16. Okay, so n is equal to 12 minus 20 and 14. We found out normal vector. Okay, the intersection between these 2 vectors is point P. So we're going to use point P as x sub 0, y sub 0, and z sub 0.
Professor, is then y negative, positive?
It's positive sign. Yes, I forgot to distribute this negative sign. Okay. Now equation of your plane is A, which is 12 times x minus 1 plus 20, y minus 3 plus 14, z minus 2 equal to 0. Before distributing these numbers, let us find the common factor between them, divide everything by the common factor, and simplify it as much as we can. This can be simplified into 6 times x minus 1 plus 10 times y minus 3 plus 7 times z minus 2. So we get 6x plus 10y plus 7z minus 6 minus 30 minus 14 equal to 0. So equation of the plane is 6x plus 10y plus 7z equals to, let's see, 20, 50 equals to. There we go. This example says find point at which the line, so the equation of the line is given as 7. Your x is equal to 2 plus 3z. Your y is equal to negative 40. And your z is equal to 5 plus t. Intersects with the plane 4x plus 5y minus 2z equals to 18. Okay. What does it ask us? You have a plane. This is your plane. And this is just a line passing through this plane at a point. Question says, what is this point? This point has x sub 0, y sub 0, and z sub 0. So it has first coordinate, second coordinate, and the third coordinate. At the point of intersection, so note that at the point of intersection, x, y, and z, x sub 0, y sub 0, and z sub 0 belongs to both the plane and the line. Okay, what's the meaning of that? It means that if you take the components of the line must satisfy equation of the plane. So, components of the line satisfy the equation of plane. Okay, so let's take the components of the line and plug them in here. X for x, y for y, z for z. It must be equal to 18. Okay, 4 times 2 plus 30 plus 5 times minus 40 plus minus 2 times z, 5 plus t must be equal to 18. This is easy to work with because you have just equation in one variable. You can easily find your t, you can plug it back in and find your x, y, and z. So you have 8 plus 12t minus 20t minus 10 minus 2t equals to 18. Okay, you have 12 minus 20, negative 8, negative 10t. Then here you have 8, negative 2, you get 20. So t is equal to negative 2. Since t is -2, it means that your x is equal to 2 plus 3 times -2. Your y is equal to -4 times -2. And your z is equal to 5 plus -2. So your x is equal to -4. Your y is equal to 8. And your z is equal to the point is -4, 8, and 30. Okay, another example for you. So this example says, find the angle between these two planes. Find the angle between these two planes. The first one is x plus 5 plus z equals to 1. And the second one is x minus 2y plus 3z, which is equal to 1. Then it says, find symmetric equation or equation of a line of intersection of L of these two points. So P, find equation of line L of intersection of these two points. Okay, let's graph these two planes. So the first one is x plus y plus z equals to 1. And the second one x minus 2y plus 3z equals to 1. So here you have two planes, and as you can see, the intersection between these two planes is a line. Our goal is to find equation of this line in part B. Okay, first of all, let us find the angle between two planes. So for part A, the angle between two planes, the angle between these two planes is the angle between the normal vectors. The normal vectors. So you know that cosine theta is defined as the dot product between two vectors, v1 dot v2 divided by the magnitude of the first vector times the magnitude of the second vector. Okay, this guy is equal to, we need to find the dot product between v1 and v2, so you all know that v1 or n1, let's call it n1 since we are working with planes. 1, 1, 1, and n2 is 1, -2, and 3. So let me change all of these to n, n1, n2, n1, and n2. So here you have 1 times 1, 1, 1 times -2, -2, 1 times 3, plus 3 divided by the magnitude of the first vector. The magnitude of the first vector is 1 plus 1 plus 1, which is square root of 3. Magnitude of the second vector, 1 plus 4, 5 plus 9, 14, square root of 14. So cosine theta is equal to 2 divided by square root of, we can simplify this, of course not, 42. You can rationalize this by multiplying both the numerator and the denominator by square root of 42. So 2 times square root of 42 divided by 42 can be simplified as square root of 42 divided by 21. So theta is equal to inverse cosine of square root of 42 divided by 21, of course in the calculator. This guy is equal to almost 72 degrees. This is the angle between these two lines. Okay, let us solve part B. For part B, we want to find equation of a line like L, which is the actual intersection of these two planes. To write equation of line like R equals to R sub 0 plus T times V, what do we need? We need one point on the line. We need 1 point, x sub 0, y sub 0, z sub 0 on the line, and we also need direction vector v. So we have two tasks to do. First, we need to find 1 point on that line, and at the same time, we need the direction vector. So note that these two planes are intersecting. To find the point, this point belongs to both planes. So it means that x, y, and z of that point belongs to these two planes. So first of all, we're going to use the fact that these two planes eventually passes through z, since these two planes passes xy plane eventually, because these two planes just continue. So z eventually is equal to 0. When z is equal to 0, the first equation is x plus y plus 0 equals to 1. What is my goal? My goal is to get rid of one of the variables. The second equation is x minus 2y plus 3z equals to 1. I'm going to form a system of linear equations and solve for x and y. So I get x plus y equals to 1, x minus 2y equals to 1. So my x is equal to 1 minus y. I'm going to plug that in here. 1 minus y minus 2y equals to 1. It means that negative 3y is equal to 0, or y is 0. So I assumed z to be 0. I found my y. I can use one of these two equations to find my x. So if I plug that in, my x is going to be 1. This is your point. So your point is 1, 0, and 0. 1, 0, and 0. We can check this one. We can type in 1, 0, 0, it is equal to 1, 1, 0, 0, it is equal to 1. This point belongs to the intersection of these two points. Now, for V, or the direction vector, we need to find n1 plus n2. Why is that? This vector is parallel to the line of the intersection of two planes. So of course, it is perpendicular to n1 and it is perpendicular to n2. So to find V, you just need to find simply the cross product between n1 and n2. This is equal to I, j, k. I is 1, 1, 1, and this is n1, and n2 is 1, minus 2, and 3. This is equal to I, 3, plus 2, minus j, 3, minus 1, plus k, negative 2, minus 1, gives you 5, and here you have negative 2 and negative 3. This is your directional vector. Okay, we have everything that we need. We just need to write equation of that one. So x, y, z is equal to 1, 0, 0, plus t times 5, negative 2, negative 3. You can leave it as it is, the vector equation of a line, or you can write it in symmetric form or in parametric form. Okay, one formula for you. Page 8. The distance d between a point x sub 0, y sub 0, z sub 0 to the plane, which is given as ax plus vy plus cz plus d equal to 0, follows the following formula. D is equal to absolute value of a, x sub 0, b, y sub 0, c, z sub 0, plus d, divided by the magnitude of your normal vector. A squared plus b squared plus c squared. For example, suppose the question says, find the distance between two planes. Between two planes, the first plane is 10x plus 2y minus 2z equals to 5, and the second plane is 5x plus y minus z, which is equal to 1. Let's graph these two first. let's graph the first plane. 10x plus 2y plus, so minus 2z equals to constant 5. And your second plane, which is parallel to this plane, it's 5x plus y minus z equals to 1. Very well. So take a look at these two planes. As you can see, these two planes are parallel to each other. You want to find the distance between these two planes. So n1, the normal vector, is 10, 2, -2 for the first plane, and for the second plane, the normal vector, as you can see, is 5, 1, and -1. If you divide these two vectors, 10 over 5 is 2, 2 divided by 1 is 2, -2 divided by -1 is also 2. So as you can see, the division between the components is equal to fixed constant. That's why we say that these two planes are parallel to each other. And you already saw that. Very well. To find the distance between these two planes, what do we need? We need one point on one of these planes and the equation of the second point. We need one point, any point. On, for example, the first plane on 10x plus 2y minus 2z equals to 5. How do we find that point? We can just say y is 0, z is 0, let y equal to z equal to 0. So 10x is 5, x is a half. 1 point on the plane. You get a half, 0, and 0. So you have your point, you have equation of the second plane, just follow the formula. D is equal to absolute value. Since it's distance cannot be negative. So a half, 5 times a half, plus 0, minus 0, minus 1, divided by square root of, and 2 is 25, the magnitude, plus 1, plus 1. Okay, the distance is equal to absolute value of 5 halves minus 1, you get 3 halves, divided by square root of 27. We can multiply by square root of 27, square root of 27, you get 3 over 2, square root of 27 times 27. We can simplify this, get square root of 27 over 18. And square root of 27 is 3 times 3, so we'll simplify this more. Get square root of 3 divided by, so 6. So 12.6, we're talking about quadric or quadratic surfaces. The surfaces including 3 variables and the classification of these surfaces along with their equations. So the very first one, if you forget about z, just forget about variable z. Z, for example, is equal to 0. You get x squared over a squared plus y squared over b squared equals to 1, which is an ellipse in two-dimensional space. If you graph it as a surface in three-dimensional space, you get an ellipsoid. Equation of an ellipsoid. In homework, in exams, you get a messed up equation and the question says, okay, identify the type of surface that you have. The second one, if you have z squared over c squared equals to x squared over a squared plus y squared over b squared, then you get equation of a cone. If you forget about variable y, if y is equal to 0, then you get z squared over c squared equals to x squared over a squared. If you take square root of both sides, you get z equals to plus minus c over a times x, absolute value of x. So you get two lines in two opposite directions, and those are the traces of cones. Next equation, you have z equals to z over c equals to x squared over a squared plus y squared over b squared. Again, if you forget about y, if y is equal to 0, just forget about it. Z is equal to c over a squared times x squared. In two-dimensional space, you just have a parabola. Parabola. So you can remember parabola. If you rotate this around z-axis, you get elliptic paraboloid. Remember equation of a hyperbola, x squared over a squared minus y squared over b squared equals to 1. Now we generalize the idea in three-dimensional space. We have x squared over a squared plus y squared over b squared minus z squared over c squared equals to 1. We have hyperboloid of one sheet. Now for a hyperbolic paraboloid, you have, it's very similar to elliptic paraboloid, but note the difference between the signs between x squared and y squared. When it's plus sign, you get elliptic paraboloid. When the sign between x squared and y squared is minus sign, negative, you get hyperbolic paraboloid. And finally, hyperboloid of two sheets. Compare it with equation of hyperboloid of one sheet. You get x squared plus y squared minus z squared. Now here you have x squared plus y squared minus z squared equals to minus 1. If you want to compare it, you get a negative 1 on the right-hand side. You get hyperboloid of two sheets. Again, you need to know all of these formulas to be able to classify equation of x, y, and z. Very well. Let's take a look at some examples. Okay. 12.6. So this example asks to identify the graphs. The first equation is z equals to x squared. The second equation is x squared plus y squared over 9 plus z squared over 4 equals to 1. And finally, you have z equals to 4x squared plus y squared. Okay. Before doing any algebra, let us graph this quickly. The first equation says we have z equals to x squared. Let's just rotate this guy. There you go. This is your graph. As you can see, the graph is including parabola. So it's a paraboloid. Take a look at the second equation. Here you have x squared plus y squared over 9 plus z squared over 4 equals to 1. Let's take a look at the graph. Okay, let's just rotate this guy. See this from different angle. As you guessed, it's equation of an ellipsoid. And finally, let's take a look at the last equation. Z equals to 4x squared plus y squared. There you go. Take a look at your graph. Let me just minimize this a little bit. As you guess, it's an elliptic paraboloid. So when it comes to these types of surfaces, try to graph them first. Then compare your equation with the classification of the equations on 12.6